Welcome, everyone, to today's Design Pioneers lecture at the Jacobs Institute for Design Innovation at UC Berkeley. My name is Bjorn Hartmann, and I'm the faculty director here at the Institute. We're pleased to welcome Dr. Jeff Rulifson to our Design Pioneers series, an ongoing lecture program that invites distinguished practitioners in design and technology to share their work, accomplishments, and legacy, much of which has directly impacted the way we live today. Before we begin, I'd like to remind you that card captioning is available for this talk and can be turned on in your interface if you're joining us through Zoom. This presentation is being recorded and will be available with captioning in the upcoming week. For any other access requests you may have, please send us an email to laurenardis@berkeley.edu, and Lauren can also paste her email address into the chat. There'll be a Q&A period immediately following today's talk. We encourage you to submit questions as they come up throughout the talk using the Q&A function if you're joining us through Zoom. Now, this is a new hybrid talk, so we have both an in-person audience in the room and an online audience on Zoom. If you are in our student audience in 310, you can submit questions either by joining the webinar through the Q&A function on your device. In that case, just remember to turn off your mic, turn off your speakers, or submit written questions to Lauren, who will then share them with us. Now, before I introduce Dr. Rulifson, I would like to invite you to join us for our next guest speaker as well. This will be Liz Gerber. Liz is a professor at Northwestern University and a founder of Design for America. She'll be joining us on September 24th as part of our ongoing design conversation series. Please visit our website, jacobsinstitute.berkeley.edu, for registration information and full details. Dr. Jeff Rulifson is a computer scientist, most famously accredited for designing the software used at arguably the most impressive event in personal computing history, known today simply as the mother of all demos. This demo took place in 1968 at the Computer Society's Fall Joint Computer Conference. This was back when all of computer science could have one joint conference, where Doug Engelbart demonstrated NLS, the online system, which had almost all of the fundamental elements of modern personal computing. It included the use of a mouse for input, introduction of hypertext, video conferencing, word processing, dynamic file linking, revision control, and a collaborative real-time editor. Jeff also played important roles in the early ARPANET, the precursor of our present internet, and in the development of the first personal desktop computer at Xerox PARC. Also, let me mention, he was the first person to hire an anthropologist. That was Lucy Suchman, right here from UC Berkeley, into a technology company. And that ultimately transformed many companies' approach to how design is being done. Over his career, Dr. Rulifson has made significant contributions to the fields of artificial intelligence, office information systems, research standards, and engineering management. He received his Ph.D. in computer science from Stanford. He's led teams at Xerox PARC, ROLM, Syntelligence, Sun Microsystems, and Oracle. On top of many awards and recognitions, he received the ACM Software Systems Award and was inducted into the SRA Hall of Fame in 2006. Please join me in welcoming Dr. Jeff Rulifson.
Okay, hi. Now, so I'm on live, right?
Yes.
Okay. Hi, everybody. I need to go into screen sharing mode. Where is it? Right here. Okay. So this is what we're going to talk about, the mother of all demos. I'm actually leaving out an enormous part of Doug's work, but we're just going to focus on this. And I thought a fun thing is to ask the question, why do we say we click on a link with a mouse? And that's basically what we're going to go into. This actually, the idea started with a professor at MIT named Vannevar Bush. And he was the father of analog computers. well, at least one of the really big people. He was also science advisor to FDR during World War II. And in that role, he oversaw things like the over-the-horizon radar project between Stanford and MIT, the breaking of the Japanese code in Honolulu, and Los Alamos, and work on the atomic bomb. And in doing all of that, he came out extremely frustrated with his ability to manage the collaboration and all of the information that he had to get his hands on to make sure everything was going well. So after the war in 1945, he wrote a paper called As We May Think. And the paper was published in the Atlantic Monthly, of all places. And he proposed a machine called Memex. And Memex was based on microfiche. His idea was to take all of the information that he could get his hands on and photograph it and put it in microfiche and have it in a desktop-sized machine that you could rapidly select things from. And he had an idea for embedded dots. And he would embed dots in the microfiche, and these dots were basically pointers to other places in this vast store of microfiche. And a user could then position a crosshair over the dots, point at it, and the machine would automatically take you someplace. So I think that's the origin of the idea. And Doug Engelbart was, I think, a sophomore, maybe a junior at the University of Oregon, and got drafted into the Navy. And he was a electrical whiz at the time. So they made him a radar technician and sent him to the Philippines. And in the Philippines, in the USO, he found Vannevar's article and he read it. And we're going to talk about what happened. So here you see the original article with Doug's notes. This is actually in the Computer History Museum. You can get a copy. It's sort of fun. And in section 7 of the article, over here where Vannevar is describing how the dots work, you see the word link. And there you have it. That's where the word link comes from. So let me talk a little bit about how Doug took this from a seaman in the Philippines to the Stanford Research Institute. Doug was very interested in both scaling and media. And he would study hummingbirds and he would study elephants and why can hummingbirds fly the way they do? Why can certain insects walk on water? And before that, I should say, he graduated from Oregon, went to Berkeley, got a Ph.D., came down to the Bay Area, down to Mountain View, and worked at NASA. And then his scaling efforts, he came up with these ideas about scaling. And one of them, he was very closely related to the beginnings of the inventions of the transistors at that time. And he invented Engelbart's law, which had to do with how we were going to be able to scale transistors and make chips. And he gave a talk on this at a IEEE meeting, and Gordon Moore came by, was at the meeting and heard it. They became friends later and turned Engelbart's law into Moore's law. And that's a whole separate story. But anyway, so Doug, in this scaling vision that he had a vision for how much computing power computers were going to have. And he coupled that with his idea about media. And he became convinced that if you had, in a sense, unconstrained computational resources available, you were going to be able to create and edit and link and store and search and render media that can't exist in the normal world. You could generate music that musicians couldn't play. You could do artwork that artists couldn't produce. And so he had these ideas gurgling in the back of his head, along with the Memex ideas, and he took those two and merged them with the idea that what could you do if you had all of the information that Bush was talking about available inside your computer, a yet to be invented computer. And that led him to a paper, a research report that had ARPA funding from the Advanced Projects Research Agency in 1962. And here you see his goal. By augmenting human intellect, we mean increasing the capability of a man to approach a complex problem situation, to gain comprehension to suit his particular needs, and to derive solutions to problems. So Doug was not out to make a better user interface, and he wasn't out to produce text editors or graphic editors. He was out to somehow produce the software for computers that would help people accomplish basically what Bush wanted them to be able to do. That is, have vast amounts of information at their disposal, coordinate it, fit it together, and solve problems. So that paper led to a very small contract from ARPA that had to do with pointing devices. And basically ARPA wanted, well, NASA administered the contract. NASA wanted advice on what to put in the capsules that were going to the moon. And Doug had the contract to investigate all of that. And over here in the corner, he looked at all kinds of things, joysticks. We had knee positioners, light pins. And over here in the corner, you see why we have a mouse. The error rates on the mouse just beat everything else out, hands down. And oh, you can barely see it. It's called a mouse because it has a tail that sticks out over here. But that's the idea of the mouse. So with that, I want to go to a sort of a personal story. I was at the University of Washington as an undergrad at the time. In fact, I was just graduating that week or the next week from the University of Washington, December of 1965. And I was sent by the university to the Las Vegas Fall Joint Computer Conference. And I was wandering around the floor on the conference, and I found this team of different people. They weren't dressed like all the salesmen and engineers I was used to. They were the Project Genie team from Berkeley. It was Mel Pertl, Butler Lamson, Peter Deutsch. I was mesmerized. I was just overtaken with what they were doing in their time sharing. And I hung out at that exhibit for the whole rest of the conference, spending a lot of time helping Peter Deutsch debug his debugger for the 940. And Doug Engelbart came by. And Doug and I sat and talked, actually for a couple hours. And he explained to me the vision from the paper, from the augmentation paper, and I got it. I just understood. So instead of going home, I went to SRI in Stanford, and making me very sentimental, by January 3rd, I'd moved my family to Menlo Park. I was a graduate student, and I was working at SRI. So that was really an amazing time. Then I went to work. Here's what I did by the fall of 1968. I had taken a small meta compiler, that is a little tiny compiler that compiles itself. It was written by Val Shorey, who was at UCLA, and I turned it into a thing we called Meta 3, which was really an extensive meta compiler. It could compile substantial, full-scale software programs. And we'd included in those not just programs like Wurst PL360 or Algol, but we had object-oriented in this and some other very special features. But it produced very sloppy code in a way. It wasn't very well optimized. So from that, I produced a one-pass compiler called Tree Meta. That was a highly optimized compiler. In fact, it was fun because I wrote an assembler for the 940 in Tree Meta, and it would assemble programs faster than Peter Deutsch's assembler. And so finally, I had TreeMeta written in TreeMeta, is the compiler written in its own language, compiling itself. And that I wrote a machine-oriented language called MOL 940 in TreeMeta. And that was a structured oriented programming language that sort of was modeled after Nicholas Wirth's PL 360. And in that I wrote NLS. I wrote the core of NLS based around a lot of ideas from Simula for object-oriented programming, from Snowball for string manipulation. I stole all the Lisp ideas for Lisp manipulation. And we also invented a user interface language. The idea was that everything the user input through the console was actually parsed by this user interface language. And the user interface language would then, as it was parsing, would in a sense compile the input stream and call on all of the core functions in the central part of the system to execute it. So that's how NLS was constructed as a program that was written in its own language. And that led to the demo. So now I'm going to actually step you through the demo some. This is Alan Kay. He's known as the father of personal computer. What you're going to see is a picture of the Civic Auditorium in San Francisco in December of 1968.
When it came time for the thing, I was quite sick, had a high temperature, and was shaking. And my girlfriend laid down the law, but I said, I've got to go see this thing. The theater of it was just out of sight. That's why it should be called the mother of all demos, because it was the essence of what you really want to do with the demo, which is just completely bowl people over with something that is not in any simple way an increment on what they know about.
So the auditorium held 2,000 people, approximately. Actually held about 3,000, but we had about 2,000 people that attended the conference. And the important thing is that the vast majority of computer research at the time was funded by the Advanced Projects Research Agency in the Department of Defense. And Bob Taylor, who was the director of that department, sent all the major, not just the major people from all of his projects at MIT and Illinois Institute of Technology and UCLA and every place. But he also sent a whole bunch of graduate students. And so he was seeding the world with the ideas behind this. Now I'm going to go on to show you some video of Doug at the conference, but I want you to watch something very closely. Doug is going to use words like documents and files, but I want you to understand that the documents are not text documents. They're not like the documents you think of today, which are sort of these linear things with the text and graphics embedded in them. The documents are a graph of nodes. That is, it's really a graph structure with nodes where each node has text and links to other nodes. And the display that you see when you look at a two-dimensional view of this highly interconnected graph is really a flattened subset of the graph. And the flattening happened by the user implementing keystrokes. So to specify how he wanted the graph flattened. And the files that Doug is going to talk about are just small graphs. And when there's a link at a node, the link points to another node any place on the system in any other file. And so you really should see NLS as a graph and node editing system, not a document editing system. So now we're going to watch Doug and the introduction to the demo.
I hope you'll go along with this rather unusual setting and the fact that I remain seated when I get introduced, and the fact that I'm going to come to you mostly through this medium here for the rest of the show. And I should tell you that I'm backed up by quite a staff of people between here and Menlo Park, where Stanford Research is located, some 30 miles south of here. And if every one of us does our job well, it'll all go very interesting. The research program that I'm going to describe to you is quickly characterizable by saying, if in your office, you as an intellectual worker were supplied with a computer display backed up by a computer that was alive for you all day and was instantly responsive to every action you had, how much value could you derive from that? Well, this basically characterizes what we've been pursuing for many years in what we call the Augmented Human Intellect Research Center at Stanford Research Institute. Now, the whole session is going to be devoted to trying to describe and present to you the nature of this program. But unfortunately, or fortunately, the products of this program, the technology of it, lends itself well to an interesting way to portray it for you. So we're going to try our best to show you rather than tell you about this program. A very essential part of what we have developed technologically is what does come through this display to us. And I'm going to start out without telling you very much about the program and just run through a little bit of the action that this provides us. So in my office, I have a console like this, and there are 12 others that are computer supplies that we try nowadays to do our daily work on here. So this characterizes the way I could sit here and look at a completely blank piece of paper. That's the way I start many projects. So with my system, that's a good start. I'll sit here and say, I'd like to load that in. So, sorry about that. So I'm putting in an entity called a statement, and other entities called words. If I make some mistakes, I can back up a little bit. So I have a statement with some entities words, and I can do some operations on these. A copy a word, say that word like copy after itself. In fact, the pair words I like to copy after itself. I can just do this a few times and get a bit of material there. And there are other entities like text. Say after there, I'd like to copy from that entity point to that point, and it'll copy it, right? So I could get myself some material on my blank piece of paper, and then I'd say, well, this is going to be more important than it looks. So I'd like to set up a file. So I tell the machine, all right, I'll put to a file. And it says, well, I need a name. I'll give it a name. I'll say it's sample file. I'll say, please output it. It says it did. And then it comes back automatically with an origin statement or header telling me the name of the file and the date and the time and who established it. And thereafter, I can always do something. I can ask for the status of a file, and it'll tell me that information. Very small file now, owned by me, last written by me very shortly ago, etc. and other interesting data in there. So we've seen how we can start with a blank piece of paper and go to developing a file. This file is one statement with a few words in it. Let's make more statements. So I'll say copy that statement. Lo and behold, I have another one. Copy that one. Another one. I can even copy groups of statements. I can say after that one, copy to move from there to there. It does. I can look at that and say, probably goes off the screen. It'd be interesting if I could ask the computer to collapse that, perhaps to show me just the first line of each of those statements. All right, please do that. So it did. This is one aspect of what we'll use over and over again through this presentation, what we call view control, where no matter where the file we're looking, we can ask it to use any one of a large number of parameters for constructing a view at that point in the file that best suits our need at the time. This one wants us to give an overview of the thing. So I'll say, well, I have this. I don't want them all to be statement one, so I'll just replace the word there with a 2. How about that one with a 3? Place to forget how to count.
Okay. So let's go on here. So now I'm going to show some videos of myself, but I want to sort of reinforce some ideas that what you're looking at is a document, really, as a graph of nodes. The nodes are contained one line each node contains a line of text and links to other nodes. And the programming language, all of the languages that were produced, whose compilers were in tree meta, were embedded in these the NLS documents, if you were, these graphs, were the programs. And so an if statement, for example, was a node with 3 links: the condition, the then part, and the else part. And that what you see on the display when you watch me now in the upcoming video, working with this program, is this flattening going on of zooming in and out of the document. So let's watch that.
I'd like now to have us bring in Jeff Rulifson from Menlo Park. We'll switch to his console. He's sitting one just like this, but working independently. Hi, Jeff. We're not hearing you very well. You're not hearing me? How about now? That's fine. Okay. All right. I'm sorry you can't see everybody here, but I can't very well either because of the lights. So we're about even. Okay. I'd like you to talk to them about the way the special languages have helped in making flexible design and study available for us of the user features, the functions, and the repertoire of the commands, as well as the control dialog for them. And then also, it'd be an interesting example here because you programmers are the ones who most intensely found use for working online as we're building up. Show them how you structured your system guide. Okay? Okay. I think we can do that. We can get sort of a good feeling for the way the whole system is put together by looking through the system guide. The file is one that system programmers sort of put together, help them get around. NLS right now is getting to be a fairly large program. It's not huge by a lot of standards, but it's getting pretty big. This picture in our system guide file is a picture of the overlay structure. Our overlays are page sizes, so they're not too big in the 940, but each label in this picture names a code file, and each one is 3 to 20 pages long. I mean, 20 text pages if you printed them out. Just to sort of show how you can use a file like this to move around in the code, and also how the code is put together. As I said, each label in the picture is the name of an overlay, which is also the name of that file, but it also happens to be the name of a statement in this file. By selecting one of these pictures and moving there.
Okay, so there you've seen me jumping around a little bit, and I'm going to show you another video, and you can sort of ignore what I'm talking about, but I want you to watch my hand and watch what happens.
So go back to that other file. Move back to our picture again and find where overlay text edit is. It's right down here, so we'll go and sort of move down through that one. The text edit overlay illustrates a lot of the different kinds of things that we've done.
So this thing down here is we called a Keyset. And Keyset had 5 switches for my 5 fingers. And our mouse had 3 buttons. So that gave me 8 bits. And so with the 8 bits, I had available to me 255 single character commands, which is a lot of commands to learn for a system. Or when I went into text typing mode, I had 255 characters available to me. So I sort of had the entire ASCII key set and the control key set. And I'd actually trained myself so I could type about 20 words a minute on a keyboard. I'm sorry, 20 words a minute without a keyboard, just using the key set in the mouse. So it was a wonderful way to sit and just work at a screen without having to mess with a keyboard. So this was clearly for augmented users. I mean, for skilled users, people that really were willing to put a lot of work into the training. But it really, to me, has made Word and Pages Doug used to talk about the idea of tying a brick to a pencil, that you take a thing that has a lot of flexibility and you make it something that isn't very flexible. And I think that's what today's systems are doing. So we old NLS users felt as if we were playing a violin and not playing a kazoo. Now I'm going to sort of give you the punchline here about what happened with this demo.
It was really a part of showing what the potential of this coming computer document construction, retrieval, linking, video conferencing stuff is all about.
I'd like now to have us bring in Jeff Rulifson from NLS PARC. I'll switch to his console. He's sitting on just like this, working independently. Hi, Jeff. We're not hearing you very well. You're not hearing me. How about now? That's fine. Okay. All right. I'm sorry you can't see everybody here. I can't very well either because the lights sort of body. Okay.
Before December 1968, computers were for computers. If you went to a computer science department, it wasn't even a part of engineering yet. Thinking of it as the way that you document and write and communicate and share with people was not part of the thinking. By January of 1969, it was part of the thinking. The whole foundation behind Apple and Microsoft and everything really went back to this demo. Technically, it was an engineering tour de force never to be repeated.
So that was actually filmed in the Civic Auditorium. Gives you more of a sense about how big it was. Now I'm going to go to Vint Cerf, known as the inventor of the internet. Vint and I worked very, very closely together. He was working on the higher level protocols that would eventually run over the ARPANET, which would become the internet. And I was the big app, was doing the app, which was to run on the ARPANET. And so we worked very, very closely. And here's Vint talking a little bit about Doug.
So he felt very strongly that people could work together in a collaborative way and that computers could assist that collaboration of augmenting human intellect through collaboration and computer assistance. So you often wonder about visionaries and why everyone doesn't share their vision. And Doug was among those whose vision was recognized by some, but not by others.
And now we're going to go a little bit more about Doug's vision.
The technical community was more resonant with the concrete realization of some of his ideas, time-sharing systems and collaborative work, information production, knowledge work, things like that. But they were focused on the mechanics of achieving this objective, the functionality. And I think Doug was seeing a much broader notion where this sort of vast quantity of human beings would be enabled to do things that they couldn't do by themselves or even in small groups without the help of computers.
Okay, and now, just sort of for a little bit of closing, this is Lenny Kleinrock, who was Vint's thesis advisor, but it's really a video with me talking some more.
Enormous ways to go. And I gave a lot of talks with Doug in the 90s, and I know he would agree with this. We have barely pierced the surface. Doug saw a world in which our media and our documentation and our graphics were merged in a way of interacting with people and augmenting their ability. And now you're beginning to see a little bit of virtual reality, but it's pretty crude. Looks like the film animation films from the 80s. It's really not there. And so what we're on is an evolutionary path. And Doug always saw this as an evolutionary path. And we're just, we're in the first, we're 49 years now from the demo. So we're barely into the first century of the evolution. We've got quite a few centuries to go before we figure this out.
Okay, so I was going to try to put together some citations and references for this, but I thought this would be better. There's a website, dougengelbart.org, that has a huge collection of papers and videos and all kinds of stuff. The video clips that you saw in color were taken from a movie called The Augmentation of Douglas Engelbart. It's available on Amazon. You can also get it on YouTube. There are about 1,000 photographs of me and the other people in the project working in our labs at SRI. The Computer History Museum has an exhibit on Doug. There are oral histories from those of us that worked on the projects, number of artifacts. The bulk of Doug's papers, all his personal notes, his handwritten notebooks, everything going back is in the Stanford archives. The mouse, the original mouse, is at the Smithsonian, and you can get the original reports from SRI. And that's it. That's why it's called why you click on a link with a mouse, and I'll stop screen sharing. And I went a minute over.
Thank you, Jeff, so much for sharing so much of the history. We'll now switch over to begin Q&A period. So for the audience that's mainly online and people in the room, please use the Q&A function in Zoom to submit questions, and I will moderate those questions, and I'll inject some of my own as well. Let me actually take that privilege of asking you the first question. That is, how far did your team's vision for the role of the technology in society go? So the technical ideas were all there in 1968. How
Right.
far did you imagine the impact of that on the world would go? And maybe what were you surprised by? What did you have in vision, and what were you totally surprised by?
What was I totally surprised by? One of the biggest surprises was how long it took to get things going. From the time the mouse was invented back around 1962 or 3, it took until we had personal computers before there was even a market for it. And the basic ideas of elaborate display editing weren't available until we had bitmap displays. So my biggest shock was how when you really have advanced ideas, you're not just doing a revision of something. It takes a much bigger and broader system in the world to get your idea in place. It's a co-evolutionary process that can be extremely complicated. That was a shock to me. I didn't realize that until maybe the 80s or 90s. I might also talk about the biggest disappointment, which was what PARC did to the ideas. The idea of augmentation got replaced by the idea of text editing and printing on a piece of paper, which is very natural for Xerox because that's what they did. So they took this whole structured document thing and sort of put it aside and came out with how to edit text so you could print it on a piece of paper. And the idea of actually helping people solve problems got lost.
Thank
and I
you.
played a big role in that.
All right, we've got, let me switch to some questions that came in from our audience. Avi asks, who were the heroic bureaucrats that okayed the contracts and underwrote the early work?
Oh boy, is that a story. So JCR Licklider was a friend of New Vannevar Bush, who was a psychologist at MIT, and he became one of the first ARPA directors. And he has some wonderful monographs that you might want to read. And one of his key hires was Ivan Sutherland. Ivan is maybe the most awarded person in the history of computing. He has the Turing Award, the Kyoto Prize, the von Neumann Award, and who knows what else. He is the inventor of computer graphics. He became a director to replace Licklider at a very young age. And I've known Ivan since 1966. I've worked for him, he's worked for me. It's been quite a thing through our lives. Ivan, in turn, left ARPA and hired a guy named Bob Taylor. And Ivan is the one that really got Doug, talked Taylor into supporting Doug and introduced Taylor into the ideas. Taylor was actually a psychologist, loved it, and was the one that put the support behind it. Those are the major names that really I want to use bootstrap, that put this thing into orbit.
Thank you. And just as a note, Ivan Sutherland, for those of you who are in Jacobs Hall, if you look out the window and look at Soda Hall, I see some heads turning. Ivan Sutherland had an office in Soda Hall for a number of years. And so when I first arrived at Berkeley, I was just, getting to know the building, walking the halls, and there was the nameplate of Ivan Sutherland on the wall.
I've done projects off and on with Ivan since the 60s.
Excellent. Okay, another question. This one is from Titus. Do you think another mother of all demos is possible nowadays, or is human-computer interaction research too saturated to concentrate on so much innovation into a single event again?
Well, first of all, we haven't finished the revolution yet. I mean, Doug's ideas are just beginning. Is there a possibility of another one? Sure. I just have absolutely no idea what it would be. And I think, that's how these things have to start. Not as a revision of this, but use smell and do something different. Nobody's done that yet.
Excellent. And for those of you in the audience who are taking my AR VR class, we're going to talk about smell in just a couple of weeks.
We used to
Turns
talk
out it's a very thorny problem.
We used to talk about smell in the AI lab at SRI and couldn't figure out what to do.
That might still be the case. Oh, which actually brings us to another question from Cyrus in the audience. What are your thoughts about new forms of human-computer interaction, such as virtual reality, augmented reality, smart speakers?
What do you mean by what are my thoughts?
Well, I guess maybe let me embellish. Do you find some of them particularly promising or aligned with the augmentation vision, and do some of them seem more gadgety than deep?
Well, in the context of Doug's thoughts, they're gadgety. Because I don't incorporate them into the way that I access and organize and link my information together. Whatever I do is sort of crude, right? Make a video, somehow glue that into the middle of a flat document. It's not dynamic, and it's not, in the McLuhan sense, it's very cold. I'm not tied into it. Maybe I'm being too harsh on people, but I want an augmentation system, not just a video editor and a text editor and then glue them together, glue together things.
So do you think that core goal of human augmentation, that might still be the guiding goal for the next 50 years? Or is there some other large vision that can also drive 50 years of research?
No, I think you could take the augmentation vision and do it over again. And when we started our tools, well, people have, as I've done other talks, somebody calculated for me once that a smartphone today has more transistors than all the computers in the world in 1968. So we were extremely limited with the tools you have available today to incorporate all of the audio, video, text stuff. better user interfaces that get me up to the kind of interface I had on NLS, so I don't have to grapple with keyboards and mice. I think you could do augmentation over again and do a spectacular job. The problem is there a market for something that people need to be trained for? And there is, in some cases, like take Photoshop, AutoCAD. They're mode-oriented editors. The interfaces take an extremely long time to learn, but if you want to do it, those are the tools. But people somehow can't take that idea and apply it to the simple task of writing about their ideas. But if you can find a way to generate a market for it, I think you really could do it over again. I've actually had an entrepreneur propose that to me, but at age 80, I don't have the energy.
So I wonder if that is true for some of the hardware innovations in your group as well. So some found universal adoption like the mouse, and then you showed the chording Keyset,
Right.
which we don't find on that many desks. Is it because of the learning curve, or are there other factors at play?
I think it's the learning curve, but I think it's the mismatch between those people that want it, the mismatch in volume between the people that would actually use it and the cost of bringing products to market and stuff like that. I've talked to the people at Logitech, and that seems to be the problem. We had chording keysets on our Altos, and basically I was the only person, well, me and Bill English, that knew how to actually run the chording keyset. So in talking with Larry Tesler one day, we had this idea, and I took Bravo at PARC, Simone's editor, and went into the user interface section and changed it around. And we took the chording keyset and we labeled the keys cut, copy, and paste.
All right.
That was the end of the high-speed chording keyset.
Yep. Incidentally, in the building at Berkeley in Jacobs Hall, there's a class taught for a number of years where students would build their own chording keysets and
Oh, great.
plug them in and demonstrate that they could type "Hello World" on them.
But could they type 20 words a minute?
Maybe a month or two later. All right, we have another question from the audience here. How large of a group in total was working on the mother of all demos?
There were about 4 hardware engineers and 4 software engineers and an administration staff. There were 12 people in the project. Yeah, maybe 5 people in software. One guy was doing OS and drivers. One was doing user interfaces. One was doing printing for flattening documents so we could print them. And then it was me, and I think Donnie Andrews wrote all the code
So
for the
quite
display.
a small team compared to the thousands of people who might work on a Google product these days.
Yeah, if you know Menlo Park and you know the Oasis, we closed the Oasis many nights.
All right, let me, we're almost at time here. So let me just ask you one final question. What career advice you might have for our students? You've had such a successful career. How much of that was a master plan you had for yourself in your head, and how much of it was serendipitous, being in the right place at the right time?
It was serendipitous. It was not a master plan. Headhunters used to try to hire me in the 80s and 90s, get me to go to another company. And a big question was, what are your goals? And I would say I never accomplished a goal that I had for myself. That what would happen is I'd step into a situation, I'd have a goal, I'd get in a situation, I'd step into it, I'd do something, and off I would go in another direction. I shipped, as an engineering manager, I shipped the world's first digital voicemail system. I shipped the world's first at ROLM. I shipped the world's first Windows system at Sun. And it was all serendipitous.
All right. So
grab the opportunities.
all right. Well, that's a great note to end on. I'd like to thank you again for spending your time with us today, and for all of you attending, either in person and online, and the engaging questions you've asked. If you'd like to listen back to this talk, it'll be available on our website in the coming days once editing and closed captioning have been finalized. So thanks again to everyone. I hope you also enjoyed spending some time with us at UC Berkeley, and we learned a lot.
It was a lot of fun putting this together. Thank you.
Thank you. Thanks, everyone.